All right, let's go ahead and get this started. Good morning, everyone, and welcome to WCEC's Affiliate and Partner Webinar Service. Today's webinar topic is Climate Appropriate Technologies. Where are we? Today's speaker is Jonathan Woolley, an Associate Engineer at the WCEC. And I am Paul Fortunato, the Outreach Coordinator here at WCEC, and your host of today's webinar. These webinars are a service provided by WCEC to help inform and guide potential energy efficiency decisions for utility DSM programs and beyond. We at WCEC hope you find these webinars valuable, as they are only offered live to our affiliates and partners who support this research. To help ensure the information in these webinars remains relevant to you, our valued partner, I welcome any and all feedback, including topic recommendations. So please do not hesitate to call me or email me with your ideas to enhance the value of these webinars. I'll be providing a contact slide at the end of this webinar, so you may quickly get in touch with me or the featured speaker. So this is what's new at WCEC. Our latest newsletter for May has just been released, and this month's newsletter includes a retrospective on water use in evaporative systems and water use in energy generation. Also included is a recap from WCEC's annual Affiliates Forum with links to the PowerPoint presentations, and last month's webinar on understanding behavior to maximize energy savings is now available to view online. If you have a question regarding today's presentation, you may ask it directly in the chat panel, or if you would like to speak to the presenter and the audience, you can request to be unmuted from the same chat panel. I'll be monitoring the questions panel and will save the questions and ask them to our presenter in the order they appeared at the end of the presentation. Our next webinar, happening in June, will feature some demonstration results for adaptive thermostats. Our speaker will be Marco Pretoni, a PhD candidate working with the WCEC. I will send out the initial invitations for this webinar within the coming weeks. This webinar will be recorded, so if you'd like a copy of this webinar, please contact me. I'll post our contact information again at the end of this webinar. Today's topic, once again, is Climate Appropriate Technologies. Where are we? And now let me welcome Jonathan Woolley. Jonathan, where are we?
Thanks so much, Paul. So for any of you that were able to make it to our Affiliates Forum, this might be a little bit of a review for you. It's most of the same presentation that I gave there, but reviewing the attendees list, it looks like most of you weren't able to make it to the Affiliates Forum, so this should be good for you. As many of you are familiar, a lot of my work over the past several years has focused on what we call climate-appropriate rooftop packaged air conditioners, especially surrounding the Western Cooling Challenge, and in incorporating indirect evaporative cooling with vapor compression cooling, both in sort of new packaged equipment and as retrofits for existing rooftop equipment. So today I'm going to not give you sort of a complete overview of exactly where climate appropriate technologies are holistically, but I'll give you more of a, say, the Google Street View perspective on a few different projects. We'll get into the grit of some of the performance that we're marking on a variety of machines, and give you our review of some of our latest understanding from those projects, our perspective on the technologies, some of the needs going forward, and some of the opportunities that are presented from all the laboratory and field work that we've been conducting. So this is kind of the overarching motivation. It was one of the reasons that the Western Cooling Efficiency Center was founded, and has been the major motivation behind the Western Cooling Challenge and the sort of climate appropriate HVAC work that we've been doing over the past several years. California's Energy Efficiency Strategic Plan was written out and updated in 2011, but has been guiding a lot of research and strategic work by utilities over the course of the last few years. One of the specific targets that they line out in the plan is to accelerate the market penetration of climate-appropriate HVAC equipment. They've got some pretty lofty goals, which I suppose is really good for a policy goals document. they want to reach to 15% penetration in the California HVAC market for new construction in 2015. And they want in 2020 that 70% of new systems installed be optimized for California's climate. So there's nowhere a clear and specific definition of exactly what climate appropriate is. But a lot of the work we've been doing in this space speaks to the idea of climate appropriate, and we've been interpreting it as sort of applying an HVAC technology strategy that performs significantly better than federal baseline requirements, owing especially to working with some of the unique climate characteristics that we have in California. Those give opportunity especially for using evaporation to improve the efficiency of HVAC operation. That can be done in a variety of ways. There's also other things we think of as climate appropriate, including operating or designing a conventional vapor compression system to have much higher effective sensible heat ratio, because as we see it, most commercial buildings in California don't need active dehumidification. They're very, very rarely controlled for active dehumidification, and frankly, much of the dehumidification that's done by conventional equipment amounts to an unneeded consumption of electricity. There's also opportunities for capturing efficiency by leveraging diurnal temperature swings in California, which are very large compared to the rest of the United States. But mostly this work has been focusing on opportunities for retrofit and replacement of rooftop package air conditioners for commercial buildings. We do see there's a lot of opportunity out there for much more integrated systems in the future, especially for new buildings. But we've really been trying to drive at some solutions that can replace or retrofit the types of systems that make up about 80% of the individual HVAC equipment currently on commercial buildings in California. And so just to point out, some of the concept of climate appropriate, a lot of our work has been focusing in on California especially, but we think that a lot of the technologies we're working with are very appropriate almost all the way across the western United States in what ASHRAE and IECC call out as Climate Zone B, which is dry and runs all the way north to south in the United States. Some of those northern states and the Intermountain West may have a lower number of total cooling hours over the course of the year, but they have climate characteristics that are similar to or even better than California in terms of their potential to leverage various forms of evaporative cooling. I think it's worth noting that there's also some interesting opportunities to apply this type of equipment outside of what we typically think of as a sort of western hot, dry climates. We're finding that even in the marine climates of California, though they are not as hot, they still have conditions that are sort of appropriate to apply evaporative cooling. And some of these indirect evaporative systems, like for example the Colorado system that we've been evaluating and incorporating in some future and ongoing research, can very well be applied in moist climates, both hot and warm moist climates, when it's applied as an energy recovery ventilator, and when you're using return air as the source to drive the indirect evaporative cooling process. There's a couple different types of equipment that enable that opportunity. And we haven't done very much research and demonstration with that, but we hope to do so soon. The main point I think that we should drive home here is that there are different and very specific opportunities to leverage the different climates in different ways. And the way that HVAC equipment typically has been applied is to think of the entire United States and often the entire world as a single climate zone that could be served by any one rooftop packaged air conditioner. So today, I'm going to dive into some details about 3 different pieces of equipment that we've had some recent success with. Number 1, I'll touch on our laboratory tests for the Munters EPX 5000, which is a dedicated outdoor air system. All of our numbers indicate that the application of this one unit on an existing, say, big box retail facility could drive 20% savings for HVAC demand during peak operating conditions. And we're right now running a field evaluation, which is in progress with PG&E and a large grocery chain located in the Bay Area. I'll talk about a side-by-side field evaluation that we've run with Walmart in Southern California to evaluate and compare the Climate Wizard and the Colorado. It's been exciting to have a side-by-side comparison. Both of those equipment are marking really outstanding performance. At peak, we're measuring energy efficiency ratio better than 40, and at part load, we're measuring energy efficiency ratios that are better than 80. It's really impressive. Both of these equipment I'll talk about later, but they're applied to cover the ventilation requirements for the space, and they do still rely on some of the other rooftop packaged air conditioners to provide for some of the room cooling load during peak conditions. Then I'll transition and talk about the dual cool technology, both review some of the laboratory results that we have from about a year and a half ago, and talk about some of the more recent field evaluations and the numbers we've been pulling from those retrofits. In short, they're showing about 40% demand savings at peak, which is consistent with our laboratory testing. And then, I'm going to summarize with each of these technologies some of the lessons that we've learned through field experience. There are a lot of challenges that we're finding with equipment. Some of them are technical challenges related to the strategies themselves. However, we're finding that's relatively small. Manufacturers have done a very good job of kind of squaring their technology out to work reliably. Most of the difficulties we've run into in the field might require institutional adaptations. They're related to providing proper maintenance, proper installation and commissioning, proper application and operation. Talk about those details going forward. So first, let's talk about this side-by-side evaluation with Walmart in Bakersfield, where we added indirect evaporative air conditioners to several existing rooftop package units. Just to review, in case not all of you are familiar with the basis of indirect evaporative cooling, the technology uses sort of a plate heat exchanger, which is integral to the operation of the equipment. There's 2 separate airflow paths. We typically call them the primary path and the secondary path. The primary path remains dry, and it usually brings air in from outside or perhaps some other source, and that air is cooled down as it passes through the heat exchanger. The cooling effect is occurring because of evaporation, but that evaporation is occurring in a secondary channel, which is wetted, and effectively the heat exchanger separates the heat transfer and mass transfer processes. So the first piece of equipment that we have installed there in Bakersfield is the Colorado M50. This is indirect evaporative system using Colorado's unique Micelan-Seco cycle. Each of the M50 units are about 1280 CFM, and in order to match the design requirements for this project, we paired them together, as you can see in this picture. The system's nice because it's modular. You can pair as many together as you need to make the airflow that you desire. So we applied to 2 and added those on as retrofit to the existing rooftop units. Remember that these systems operate as 100% outside air. They're variable speed, so they can adjust to different ventilation airflow needs, and at the same time they can allow for a very efficient part load operation by running the fan at part speed. Colorado, you should note, doesn't use a sump. It's a sort of once-through system. They measure outside air conditions and make a sophisticated prediction about how much water will evaporate and how much water is needed to wash away sort of a high concentration of minerals so that they don't end up with solid deposition inside the heat exchanger. And then that water drains out of the heat exchanger and down the drain. So Colorado's cycle looks a little bit like this. It's different from that simple fundamental model that I described for you. Even this is kind of a hacked version to explain the way that their heat exchanger is working. They've put some really smart thought into the exact layout. But I think this captures a good idea to help folks differentiate the way their heat exchanger works overall, separate from the way that some other indirect evaporative heat exchangers work. They bring in outside air through that primary channel, and instead of allowing all of it to pass through to the product side or the supply air side of the system, some of that air, as it cools down, is scavenged and carried over to the secondary channels. It comes in at a wet bulb temperature that's lower than the outside air condition, and then passes through the secondary channel in contact with water, allows evaporation, and doing the process in this way allows you to drive to significantly lower temperature for the outlet, the product, or the supply air on the primary side of that system. Under certain scenarios, they can definitely reach below the wet bulb temperature for that product air. The Sealy system is the second piece of equipment we installed. It's very similar in many respects. It's a little bit larger, 2,500 CFM indirect evaporative system. So in this like-for-like comparison, we were able to install one Climate Wizard and compare that almost directly to two of the Colorados. The system is also 100% outside air and also variable speed, so it has many of the same part load capabilities as the Colorado. This system uses a sump and recirculates water across the heat exchanger, and the sump water quality is controlled using a conductivity sensor, and their onboard controller makes a decision about when to bleed or dump water from that sump, and then the level of the sump is maintained using like a level sensor. The Sealy system also recirculates some of the air from the dry channel to the wet channel inside the heat exchanger, though you should differentiate their approach from Colorado's, especially by the fact that they allow all of the primary air to pass through that dry channel before taking a portion of that air and recirculating it to the inlet of the wet channel where the evaporative process occurs. Of course, evaporation occurs in that channel and drives the cooling effect for the dry channel. So you'll see the results, but they are also able to drive below the wet bulb condition of the inlet air under certain scenarios. So it's been a real privilege, I must say, and I want to give lots of thanks to both manufacturers, to PG&E, and to Walmart, who have all facilitated this evaluation and experiment. It's really rare to be able to do a side-by-side comparison of two emerging technologies in this way. Sometimes it can be challenging for folks out there that want to look at and review different technologies to compare separate reports and make a smart decision about the similarities and differences between the technologies. So to be able to put them both on the same rooftop and control them in the exact same way has been a really awesome opportunity. To accomplish the integration was, I'd say, a little bit complicated, but we managed to find a decent way to do it, and in doing so outlined a lot of lessons for us about the way it could be done better in the future, some of the technical challenges for how to integrate indirect evaporative coolers with existing building HVAC systems. So here's the strategy that we took. You'll see on the right in black schematic diagram of an existing rooftop unit, the DX cooling coil and a heating coil, the draw-through system with a conventional blower. These retrofits started with a Linux Stratigo system, which is multi-stage and already has a VFD to drive the fan to variable speed. That was very helpful in enabling the way that we applied the system. If one tried to replicate this with a conventional rooftop unit, you would probably also need to consider including VFD drive for the fan. So we added the indirect evaporative cooler to supply product air, actually into the return plenum of the rooftop unit. In doing that, we had to install gravity relief dampers in the return plenum to avoid driving product air from indirect evaporative system through the return distribution system of the building. We wanted to drive that flow through the rooftop unit, through the supply distribution system, and utilize the existing ductwork and diffusers to get the air out into the space in an appropriate way. We wanted to utilize the existing dampers in the system so that we could make a decision about when to allow airflow from the indirect evaporative system, and when to allow some airflow from outside air, when to allow some airflow from the return. It's important to note here that we added this equipment onto existing 10-ton units, and the nominal airflow required for vapor compression operation in each stage is quite a bit larger than the product air coming from each of those indirect evaporative coolers. So we needed to maintain that when we also needed to provide DX cooling with the rooftop unit, we could draw some portion of return air instead of relying only on the airflow coming from the indirect evap system. So in order to accomplish all of those things, we also had to add a new damper into the product air plenum of the indirect evap system, so that we could sort of meter the airflow and maintain appropriate pressure in the product plenum, while also allowing the rooftop unit to draw an appropriate amount of return air or outside air as needed. One of the unique pieces of this design is that we decoupled the return air damper from the outside air damper and added a new actuator on the outside air damper so that we could allow the unit to operate in economizer mode during those periods when the indirect evaporative cooler is not able to maintain all the room cooling conditions, or when indirect evaporative cooling isn't needed, say in the heating season when the system has been winterized and shut down. In that scenario, you still need to provide ventilation air to the space, and so we needed to make sure that we had access to that outside air through that outside air damper. This kind of gives you just an airflow schematic of how the system would be operating when you need some DX cooling. The VFD ramps up on the supply blower for the rooftop unit, draws some return air from the space. The fan and indirect evaporative system is operating, which is providing some air into the return plenum there. The pressure in the return plenum is negative, so that you'll draw air from the space into the rooftop unit. But it's important to note that the pressure on the outlet of these indirect evaporative systems needs to be maintained positive and within a particular range. That's very important for folks to realize. We've seen a variety of different customers and applications where they've tried to add the indirect evaporative coolers onto rooftop package units, but haven't made the provisions to to keep that at a positive pressure, and the system may still work, but the performance will definitely suffer. The best way you can think about it is that if that product plenum is under negative pressure, you can start to cause some imbalance in the airflow between the primary and secondary channels, and even perhaps draw air backwards through the secondary channels, which is not what you want to do. Here's what everything looked like at the end of the day for the Climate Wizard system added onto the rooftop unit, for the Colorado system added onto the rooftop unit. We're very pleased it was a pretty clean installation. I do think, though, it's important to note at this point, now that I've explained the strategy we applied, we think it is a little bit complicated. In fact, we had to... I'm sorry, Paul, are those not updating?
It doesn't look like it. I don't know if it's... Is it updating for anybody else? If somebody else could post in the chat, see if you see a photograph right now instead of the diagram. Okay, thanks, Steve.
Let me
see if you can press back. Yeah.
There it
goes. Okay.
All right. Well, you missed the slide in between that showed the Climate Wizard, but this is basically what both of the retrofits looked like. As I said, it turned out pretty clean. We're very pleased, though I do think it's important to note at this point, now that I've explained the overall function of our retrofit strategy, we think it's a little bit too complicated. We've talked with Walmart about the performance marks of the system. They seem to be very impressed with the performance numbers that are coming from this, but they don't seem ready to gobble up the equipment and install it everywhere. I think owing to the fact that it took a lot to integrate. UC Davis actually had to develop a custom controller to take all of the 24-volt AC inputs from the building management system and map them over to control the indirect evaporative and the rooftop unit in this combined way that I've described appropriately, and to sequence them appropriately so that the indirect evap system has priority when it should have priority, but economizer cooling and ventilation is still supplied when the indirect evap system is off. There are, we think, some simpler ways to do this going forward. I'll discuss those a little bit more detail later on. So, in summary, as I get into the results here, both of these pieces of equipment mark out really fantastic performance, and lest somebody think that a head-to-head competition has to end with one manufacturer rising as the champion, really the conclusion here is that it's too close to call. I'm frankly surprised by that. There's almost always really significant differences, and there are significant differences in the operation and some of the characteristics of these machines, but overall their energy performance is very similar. Everyone wants to think of performance of evaporative systems based on the wet bulb effectiveness. Some folks call this the saturation effectiveness. It's the nearness to the inlet wet bulb condition that's achieved by the product air or the supply air at the outlet of the system. So this chart shows wet bulb effectiveness as a function of the outside air wet bulb depression. I apologize, actually, that's not the correct axis label. It's outside air wet bulb depression, which is the difference between the outside air temperature and the outside air wet bulb temperature. And you can see that the Colorado is marking between about 70 and 90% wet bulb effectiveness at full speed, and a little bit higher wet bulb performance at part speed. The Climate Wizard is marking between about 70 and 100% wet bulb effectiveness at full speed, and its part speed wet bulb effectiveness increases pretty significantly. Some of those numbers are actually above 115%. So don't be too quick to make a conclusion about about the performance of these systems from these numbers. It's important to realize that with this indirect evaporative heat exchanger strategy, you can achieve a higher wet bulb effectiveness by sacrificing some airflow and by using more fan power. So when we actually look at the coefficient of performance for these systems, they look much more similar. So again, I'm charting this time actually by outside air temperature. We're looking at the COP of the system. The marks in black show full speed operation, and the marks in blue show part speed operation. I think I failed to describe that the way this equipment is installed on the store is so that when operating at part speed, which was about 75% airflow rate, these 6 units operating in parallel provide for the entire 12,000 CFM of required continuous ventilation for the sales floor. And when there's an additional call for cooling from the store, the equipment ramps up to full speed, 100% airflow and an increased capacity. So in those hours when you can get by with the cooling delivered at part speed, you can run with a coefficient of performance that's well above 20 in time, and is actually increasing, you note, as outside air temperature increases. When you need the additional cooling capacity at full load, I think we can expect sort of at full load at peak, which goes beyond the data that was available during this time period. The trend shows you should mark coefficient of performance around 15.
Where would a standard unit line up?
In the field, we've been marking coefficient of performance for standard machines around 2. Yeah. All right. Then you can see that the system sensible cooling capacity for the machines is also very similar. I won't go into too much detail about some of the nuances, differences between them, but our report on this project should be coming out and published through PG&E and ETCC within the next several weeks. It's also important to remember that we've applied this equipment to provide for all of the ventilation in the space. Under all conditions that we've experienced, they're able to cover the entire ventilation cooling load. So that is, they're able to take all of the ventilation air, even at peak, and bring it down at least to the room conditions, and almost always below the room conditions. When you are supplying air below the room conditions, you're also providing some sensible room cooling. You're affecting the temperature at the thermostat in a positive way. And so we can look at the capacity for sensible room cooling. And this is the way that you might look at the system if you were thinking of replacing a recirculation-only system. And so it's important to remember that the capacity, and you'll see the coefficient of performance if you look only at the room cooling, actually decreases as the outside air temperature increases. The system's total capacity is increasing significantly as outside air temperature increases, so it's doing a great job of cooling as cooling ventilation air, but the capacity that's being sort of impacting the thermostat in the space is decreasing as outside air temperature increases. So, of course, your room loads also increase as outside air temperature increases, and that sort of that adds up to the fact that you'll need some sort of supplementary cooling at peak in most applications to cover all of the room loads. In this case, of course, we have the DX on board that unit, plus all of the other DX units on the store operating in recirculation only to cover those room loads. I won't go into much detail here, but we've resolved the performance of these systems out to a very good level of detail. Along with those wet bulb effectiveness charts, you can see from psychometric results that that the supply air temperature from the Climate Wizard is typically somewhat lower than the Colorado, even though the total cooling capacity and efficiency are very similar. When it comes to water use from these machines, we mark out some numbers that may seem at first glance pretty high. Each of those units, so each rooftop unit, is for the Climate Wizard using between about 75 and 150 gallons of water per day. Colorado's marking out between about 150 and 300 gallons of water per day. The gold bars on top of the Climate Wizard system here show how much water was drained. It looks to us like Climate Wizard's doing a really good job of sort of constraining how much water they're putting down the drain, and their control system for that we admire, and we think they're doing a very good job. Unfortunately, our drain water sensor for the Colorado wasn't functioning, so we have the total water consumed by the system, but we weren't able to mark out what fraction of it is being drained. Now, it's important to normalize those numbers by the total amount of cooling that's being delivered by the system, and put it in terms of gallons consumed per ton-hour of sensible system cooling. For the Climate Wizard, we're looking at between 2 and 3 gallons per ton-hour consistently over the entire period of evaluation. The Colorado is marking out more like between 4 and 5, some days up to 6. So these numbers are consistent with the targets put forward by the Western Cooling Challenge for gallons of water consumed per sensible ton-hour. The retrospective look at one of the papers we wrote a little while ago on water use efficiency for evaporative systems explains sort of the impacts of water use on site relative to water consumption for power plants, and sort of provides a framework for thinking about how and whether or not the water consumed on site by evaporative cooling saves enough energy to make water consumption net zero when looking at the entire overall life cycle environmental impact of these systems. So the project was really successful, but there were some challenges. As I named before, the system was pretty complex to retrofit, and we think that there's some opportunity to apply these systems more in a standalone application. They may still need to operate in parallel with vapor compression systems to provide enough room cooling, but it might be easier to install them almost in a DOAS fashion, a dedicated outdoor air supply fashion, where they stand on one end of the building and supply all of the ventilation air, and then all of the rooftop units on the building are constrained to operate in recirculation only. It'll avoid all of the complex physical additions that we had to provide to these 6 rooftop units, though it'll still, very importantly, require some sophisticated controls integration. Controls contractors should be able to do this, but it does require a different type of control strategy that makes a smart decision about when the whole building should run in economizer mode, when it should run in indirect evaporative cooling, and to make sure that it's always providing for enough ventilation, even during those periods in time when you don't need cooling, and in fact when you need heating. I said before, the system performance for this equipment is sensitive to downstream pressure. That's a biggie. We've seen a couple of different applications that have had that trouble. Ours included. In fact, on one of the units, our control system sort of failed to maintain appropriate downstream pressure, and performance on that one piece of equipment suffered significantly for it. And then the most significant challenges were really related to commissioning and maintenance. For example, because these units are bringing in 100% outside air, and applied in Bakersfield, in fact, which has terrible outside air quality, the filters loaded very quickly. In fact, in hindsight, we think that they need to be replaced about every 30 days. which is consistent for recommendations from the manufacturers and both these manufacturers and others. But it was sort of difficult to get that done correctly, you could say. Also, we experienced some freeze damage during the period of time this winter when we dropped well below freezing for a few days, and that really shouldn't have happened if the equipment was being maintained and shut down appropriately during the wintertime months. But the folks that were supposed to be doing that didn't manage to do it. So those are some challenges going forward. I mentioned the opportunity to install these things in parallel instead of series. We think that they can, should, and actually are being integrated into unitary DOAS equipment so that they don't have to take the same form factor you see, but could exist as a heat exchanger within a larger unitary air handler that commercial buildings are more familiar with and which are readily integrated into existing building management systems. And also to note that the Western Cooling Challenge has always held in mind the need for integrated and packaged hybrid air conditioners that can replace rooftop units one for one, have indirect evaporative cooling plus vapor compression integral. So the next project I want to talk about technology is Munters EPX 5000, which is a hybrid dedicated outdoor air supply system. We ran laboratory tests of this equipment with PG&E at their Applied Technology Services Test Lab in San Ramon with Robert Davis, who I suspect many of you are familiar with. We're pretty excited to see this piece of equipment. It is a unitary hybrid dedicated outdoor air supply system that incorporates indirect evaporative cooling with vapor compression. Here's a good outline for how the equipment works. It's designed to bring in a continuous and steady supply of fresh outside air to provide for all of the ventilation needs in the store. That comes through a fan and passes through the dry channels of the indirect evaporative heat exchanger. When indirect evaporative cooling is enough to cover all of the room cooling loads, that's the only mode the equipment will operate in, and supply air passes to the space. When there's a call for, say, second and third stage of cooling from the space because room temperature is rising, the equipment will kick on a vapor compression system. Outlet air from the indirect evaporative passes through a vapor compression evaporator, and it's subsequently cooled. The equipment includes two stages of vapor compression. The equipment is very interestingly designed to use return air from the space as the secondary airstream to drive the indirect evaporative cooling process. This is advantageous because the room conditions are cooler than outside air conditions and typically have a lower humidity ratio. So you get to start from a point that's much better to drive an evaporative process. It already has a much lower wet bulb temperature. The system can also be configured to operate using outside air on that secondary side of the heat exchanger when it's applied in a building that needs more positive pressure and doesn't have that secondary airflow available. For example, if it were installed in a grocery store, many grocery stores also include plenty of exhaust ventilation for their kitchens and their bakeries and their pizza ovens. The ventilation supply for the sales floor is typically used as the makeup air for all of those exhaust systems, and in that application there's generally not enough return air, quote, available to this unit without depressurizing the store. So in that application, you would use outside air instead. Our laboratory tests did a really good job of mapping the performance using return air conditions and also outside air conditions over a variety of airflow rates and across a whole range of psychrometric points. Here's what our design of experiments looked like. We tried very carefully to map a broad range of space. This is actually the same design of experiments that we're using for for all of our laboratory tests of this type of equipment now. We're using the two Western Cooling Challenge performance conditions, the peak condition and the quote annual condition, which represents like a warm, dry day in California climates. And then we're also trying to replicate AHRI's 100% capacity condition used for EER and the IER metrics, as well as the part load conditions used by AHRI to capture their IEER, the Integrated Energy Efficiency Ratio performance for commercial equipment. A couple other points that also map from other ASHRAE methods of test. We've got a pretty standard map we're using to evaluate the equipment, and we've marked out performance for the system in all modes of operation. You can see the way we've charted here. At each outside air condition, we're plotting the supply air condition. That's the net supply air condition, so what would actually be supplied to the space, including the fan heat, at each of the different modes of operation. So you can see at peak, 105 degrees, 73 degrees wet bulb. Indirect evap cooling on its own can drive the supply air down to about 82 degrees, and when you need additional cooling, you can turn on first stage of DX to get down to 71 or second stage to get down to 63. I'm going to skip through a couple of these slides just for the sake of time, but you can see that we've mapped out the performance of this equipment to very, very clear marks. We're using a metric we call the indirect evaporative effectiveness to describe sort of the wet bulb effectiveness of this machine. It's the same in concept, except it's using the wet bulb temperature at the inlet from the return air from the inlet to the secondary stream, because really that is the theoretical driving potential for this indirect evap system. And relative to that number, it's achieving about 60% effectiveness. Good. We marked out, of course, power draw, and the equipment is achieving, again, very high efficiency marks. Just to look at peak performance at 105 degrees, indirect evaporative cooling only is marking out with an EER well above 30, and even indirect evap plus DX2 is marking out with an EER almost of 20. We have a question, Paul?
Yeah, there's a question here from Brad Aker. Why were there more DX or red dots with the Colorado?
It's a good question. I'm glad you caught that. I didn't point it out. There were a bunch of red dots. Should I fly back to that?
Sure. Hopefully the thing will catch up to you.
Okay. Look at this one, coefficient of performance per sensible cooling. Yeah, those red dots are showing when the combined system is operating in indirect evaporative plus vapor compression. There's even some yellow dots, which you can see in there, where we're running indirect evaporative plus DX2, second stage compressor. And what we're marking here with those red dots is the coefficient of performance for the indirect evaporative cooler. We're not marking out the combined coefficient of performance for the overall system, which we could also do with all the performance data we had, but we've kind of constrained our evaluation to the indirect evaporative equipment alone. So, Brad, I suspect you're kind of getting to the question of whether or not the Climate Wizard is doing a better job of carrying the load and therefore doesn't need to run with vapor compression cooling. The answer is no, and it's not conclusive. Each of the zones served by these equipment are significantly different. That's one of the main points we're learning from all this field evaluation. You should be strategic about where you're applying some of these indirect evaporative retrofits. When you look at a big box store, there's some rooftop units that never run. Literally, very, very few hours of the year will their compressors ever turn on. They may even be running their fans continuously to provide ventilation to the space, but somehow the load in that zone is carried by another unit, or the load in that zone is very low because there's very few people or very few lights or equipment or what have you. So we can't make any conclusions from our evaluation here about any differences in the capability for these things to offset compressor runtime hours, because they're serving different spaces even though they're controlled in the exact same way. I'll also admit that there was a little bit of a failure in the way that we controlled these systems, which we only recently found, which wasn't allowing the compressors to turn on for all of the Climate Wizard systems, except for after the second call for cooling persisted for a very long time. And typically, by that point in time, the load in those zones had been covered by one of the other systems. I see there's another question about our design of experiments and wondering why we didn't mark out performance at 115 degrees. Yeah, that's marked out as sort of a peak operating point, especially by DOE's rooftop unit challenge. We didn't include it here mostly because there's very few locations in California that will reach 115 degrees. We think that you can extrapolate fairly well for the performance of the indirect evaporative system out to that point, and honestly, we just had to constrain the number of points and tests that we had included here. Okay, so in conclusion with the Munter system, we took all this performance data and mapped it into a scenario comparison where we thought of it being added onto an existing big box store to offset all of the ventilation requirements. So just as with the Colorado and Climate Wizard, the unit almost always covers all of the sort of ventilation cooling load, and most of the time also provides some room cooling. So all of the existing rooftop units can operate in an auto mode where they only have to turn on to circulate air when there's a call for cooling in their zone, which can save a considerable amount of annual fan energy. And they don't have to carry their ventilation loads, and their room cooling loads are reduced because the additional cooling capacity from the DOAS system is carried across the zones in the store. So our scenario comparison suggests that adding this one piece of equipment onto a store would achieve 20% whole building on demand, on peak demand savings. Which is exciting, pretty significant for needing only one system to do it. Skip through that, and we're running a field test in San Ramon on a grocery store. We'll have results from that. We expect by the end of the summer season. Again, there were some challenges with this equipment, especially related to operation of the system in sequence with other rooftop units. We found that sort of the thermostat for the equipment wasn't placed properly when it was first installed. The other existing rooftop units were in very poor and sorry state. The folks that commissioned the equipment and provided for air balance in the store didn't bother to shut down all of the outside air dampers on the existing units, and we're actually somehow thinking of this unit as offsetting a direct evaporative makeup air unit for the store. So we have spent a significant amount of time working with them to train and teach them about the intention of how this unit should be operating. We've worked with them to retrofit all of the existing equipment with new economizers and to appropriately place the thermostats and control the sequencing for operation of this system as priority over operation of the vapor compression systems on the store. And then I want to lastly talk about the dual cool. Remember that the real target for the Western Cooling Challenge was to introduce hybrid packaged rooftop air conditioners, and so we were really excited about 2 years ago now when Trane partnered with Integrated Comfort to introduce and have us laboratory test the Trane Voyager dual cool system, which does exactly what we were hoping. Performance of those laboratory tests showed at peak that the system would capture about 40% savings, a little bit less at our annual conditions, but very effective. It's exciting to see that. In the last year and a half and 2 years, I think it's important to note that Trane is still involved. However, the dual cool system is being manufactured by the developers, Integrated Comfort, and it's available to be integrated with any rooftop package system, new or existing. So it's not really limited to the Trane alone. The Trane is still working to provide it as an addition to some new systems. So if you're looking for more information about the dual cool technology, look directly to Integrated Comfort. For folks that aren't completely familiar with it, here's an overview diagram of how the dual cool works. You have a vapor compression circuit marked out here in orange with your condenser on the right-hand side, the evaporator coil on the left-hand side. Typically, that evaporator coil would be covering the cooling for a mixture of return air and outside air, and you'd be bringing outside air across the condenser coil. In this case, we're pre-cooling the condenser air as it comes in from outside with a direct evaporative media. The water from that system is cooled down very near to the wet bulb and is collected in a sump. And that sump water, which is cold, is circulated around to the other side of the unit and through a water-to-air heat exchanger placed in the ventilation air stream. So it cools down the ventilation air as it enters the unit and reduces load on the evaporator coil. That warmer water is brought back to the top of the direct evaporative media, and it's cooled as it passes across the media in contact with the condenser air. So as I said, we laboratory tested the system with good performance results, and more recently we've been running a handful of pilot field evaluations. I'm going to show you some results from a full-scale roof sweep with a big box retail store in Southern California. This is what the equipment looks like installed on a piece of Linux equipment. Note that for this system, it's been installed on the outer end of a sort of paired V coil for the condenser. It's very difficult to add the evaporative pre-cooling to the inlet air for the second stage condenser, which is coming in through that little triangle there. But we're able to cover the air that's coming into the condenser for the first stage, and then also for the third stage on these units that are actually 3 and 4 stages. One really important thing to note, which I had mentioned a little bit previously, is that there's differences, significant differences between all the different rooftop units on this store. We can see that for the unit on the left, the system runs in DX2 continuously. We're marking out here as a function of outside air temperature the cumulative time spent in each operating mode. So orange shows when we're running in DX2, and the blue shows when we're running in DX2 plus dual cool. The dual cool runs when it's warm enough outside. You can see it changing over there at about 70 degrees with fair consistency. That system runs in DX2 all the time, 24 hours a day. It never turns off. The unit on the right has a much broader diversity of operating modes. You can see for a significant portion of time it's running with the dual cool only while the system is running in ventilation. The compressors aren't even running. And then also a significant portion of time running in first and second stages. Note also that there's this red blip in the top, in the middle of the chart. This is a funny mode that we've observed on a lot of the dual cool units when the pump runs while the entire unit is off, which isn't very effective, and amounts to a little trickle of energy used to circulate that pump. But it can account for, in this case, hundreds of hours over the course of a single month for some units. So we see that as one small opportunity for improving the system, maybe through some integrated control schemes. We see a significant coefficient of performance increase for the dual cool. This shows also, well, this doesn't show comparison to baseline. This shows coefficient of performance for two different dual cool units on the rooftop. One of the things to note is that there are significant differences between rooftop units. In fact, one of the big conclusions from this study is that these type of retrofits really should be installed in cooperation with sort of a quality maintenance or retro-commissioning program. We found that the airflow rate for a lot of these systems is far lower than it should be. There's issues with economizer operation and issues with charge for the refrigerant systems. Now, all of that is about the baseline equipment. It's not a problem with the dual cool equipment, but it does cause performance to suffer. These you see are two different dual cool systems with significantly different coefficients of performance because of the baseline equipment to which they're added. When we compare some of the baseline units, which we didn't add dual cool to some of the dual cool units, we do see a pretty marked increase in performance, which appears to be pretty similar to all of our laboratory testing. However, it's important to note that while there's significant differences between the units, it may not be great to compare one unit without the dual cool to one unit with the dual cool. So this actually shows the same as the last one. I'll skip by it, but what we managed to do was run for a period of time where we removed the dual cool equipment and measured, because all of our instrumentation was in place, measured the performance of the baseline vapor compression system. This shows RTU7, that one unit that runs consistently in DX2 regardless of anything. I wonder if it's not, frankly, just jumpered to run in DX2 24/7. And when we do this, we can measure out directly the impact of the dual cool, and again we see that significant increase to coefficient of performance. For the sake of time, I'm going to skip past that slide and run towards a little bit of our conclusions. I think it's one of the biggest values I find from running field demonstrations is to get to work hands-on with this equipment and develop an understanding for the ongoing maintenance and operation needs, the technical challenges with system integration and controls. I trust our laboratory tests and measurements pretty well, but that might only be, a third of the battle in trying to get towards efficiency improvements for commercial HVAC. So just one example, this is what the media looks like up close and personal the day that it is installed. It's very nice. It's very clean. This doesn't look so good. And I show this slide, I'm sure, much to the chagrin of the folks at Dual Cool. However, I think it's important to note that while this isn't looking especially successful, the performance of that equipment, which is not the pilot that we ran, this is another pilot that I visited, the performance of the system is still standing up. And the reason that there's so much scale and, in fact, algae growth on the system is because the system was not being controlled properly by the customer. Not that it wasn't being maintained, because this could be washed and everything seasonally. It's because it wasn't being controlled properly. The set point for the dual cool system was too low, so it was never turning off during the middle of the night. It was running even when it was only 50 degrees outside. The media was never allowed to dry, and when the media was never allowed to dry, it provided this perfect basis for growth and solid deposits. after more than a year of operation, this is what the dual cool media looks like when it is controlled properly. So I think the point here is that we know that we can capture good energy savings with all of these equipments. It's very important that we make sure that they get deployed properly. I think that it's wise to draw some parallels between the type of equipment we're trying to introduce here and some of the challenges that were experienced by technologies like solar thermal more than 30 years ago. That technology is great. It's very efficient, and you can capture a lot of renewable energy. But if it's not applied correctly, like, for example, if you don't take care to avoid freezing, the equipment will fail, and it'll be torn off the rooftop. We're working with, I think, again, a sensitive technology here that has to be applied appropriately. So there's challenges in the designs for our utility programs that may support these things, for our codes and standards that can provide prescriptive guidelines for how to proceed with the equipment, and for general understanding within this industry about how to work with and manage them on an ongoing basis appropriately. Those are some of our conclusions, which I discussed, and a few more which I'd be available to discuss with anyone later on if you'd like to catch up about some of our lessons learned offline. For the sake of time, I think I should skip through the rest of this and just ask if there are any more questions from folks out there before we conclude.
Thank you, Jonathan. Looks like we have a question from Brad. Please talk more about the use of a Colorado as an HRV. Any papers on this concept?
I don't know of any papers on the concept. It's actually a brand new product that Colorado's introduced. I've been talking with them about the opportunity to do this for about a year now, and as I understand, they're currently collaborating with Carrier to provide their indirect evaporative cooling modules in a way that will be integrated as a component on a standard curb for some of Carrier's built-up units, and it allows the Colorado to be used in a way that's pretty similar to what I described for the Munter system, where return air is drawn into the secondary passages for the Colorado heat exchanger, and outside air is drawn into the primary passages. So you're using return air as the starting point for that indirect evap cooling process, and because it's, of course, lower wet bulb, you can achieve much better effectiveness for the system. And then during the months where the Colorado is dry, the water's been drained out because you no longer need ventilation cooling, that same system can operate as a heat recovery ventilator inside that sort of DOAS air handler. So you can follow up with me more later on if you want to learn more about that. I'll put you directly in contact with the folks at Colorado who've made some estimates on annual energy savings that you could expect from this type of system in a variety of climates. And they have definitely introduced the fact to me that this could allow for broader geographical application of indirect evaporative cooling, because the return air is always maintained at comfortable low humidity conditions. If the system is using return air as the source, then you're always going to capture good effectiveness for indirect evaporative cooling. Very strange to think about that, but it appears like a good opportunity. Any other questions? We'll hold out for just a minute if there's any other questions. But otherwise, thank you everyone for joining us. apologize if I kept us about 15 minutes longer than than we hoped, but I appreciate you listening in. We've got a lot to share about this. All the reports for the projects will be available through our website, and each of those will also be published through the Emerging Technologies Coordinating Council.
Great. If you have any other questions for Jonathan after the meeting, that always happens to me, where I hang up and I say, wait, I have anyway. In that event, please go ahead and contact him. Hopefully you can see the contact information up here. And if not, all of that contact information is available on our website. So I wanted to thank you all again. Mark Cherniak, I'm glad it was worth it. And I hope to see you again for our next webinar. Take care, everyone.